Okay, so this week we talked about the fundamental theorem of calculus, both parts. And the worksheet, well, the first problem covers the second part of the fundamental theorem of calculus, so we'll talk about that now, and the first part later. So the second part of the fundamental theorem of calculus says all we need in order to find a definite integral is an antiderivative of the function that we have. So we need an antiderivative of this function, and we need to evaluate it at the two endpoints and subtract. So we have three things added together. We can find this piece by piece using some power rules. So for x cubed, we have 1/4 x to the fourth. 3 plus 1 is 4. So a fourth x to the fourth. 12 and 1/4 makes 3. Well, make 3. So we get 3x to the fourth. For the next one, the exponent is 2. 2 plus 1 is 3. So we get a third x cubed. The last one's a constant. The derivative of 3x is 3, the constant rule. And we need an antiderivative. So I'm going to choose the one where the constant of anti-differentiation is 0. Well, the constant of indefinite integration, I should say, is 0. And we're going to evaluate this from -2 to 1. And this notation just means we're evaluating from -1 to 2. We evaluate, this notation means we're going to evaluate this at 2 and then subtract what we get when we evaluate at -1. Evaluate this at 2, and what do we get? At 2, 2 to the fourth is 16. 16 times 3 is 48. 2 cubed is 8. 8 times a third is 8/3. 2 times 3 is 6. And now we want to subtract what we get when we evaluate at -1. -1 to the fourth is 1. 3 plus 1 is 3. -1 cubed is -1. -1 times 3 is -3. So what do we get here? Well, I'm going to combine all the whole numbers and combine thirds. The whole numbers, what do we get? 48 plus 6 is 54. In here, we have a 3 minus 3, so that's 0. So we get 54. And how many thirds? We have 8/3, negative 1/3. 8/3 plus 1/3 makes 9/3, which is 3. And 54 plus 3 is 57. Does anybody have any questions on this one? And in this step, we can check our work by taking this derivative. The derivative here is 12x cubed. Derivative here is just x squared. Derivative there is 3. Part B, integral 0 to 2 of 4x cubed minus 3x minus root x, which I'm going to write as x to the half because I know I'm going to need a power rule eventually, plus 1. Well, again, we're going to do this piece by piece. And what do we get? Well, for x cubed, again, we get 1/4 x to the fourth. 1/4 and that 4 make just 1 x to the fourth. For the next one, we have a half x squared with a -3, making -3 has x squared. For the next one, what do we have? Well, power rule with the exponent equal to 1/2. Well, we need a half plus 1. 1/2 plus 1 is 1.5. 3 halves. So we get x to the 3 halves the coefficient in front of it is, what is it, 1/3, which is another way of writing 2/3. So we have 2/3 and a negative. And for this one, we have the constant rule. The derivative of x is 1. We're evaluating here 0 to 2. Before evaluating, we can check our work that we do have a correct antiderivative here. Derivative of this is 4x cubed. Derivative of this is negative 3x, because the 2 and the 1/2 cancel. Derivative here is negative x to the half. 2/3, 3/2 cancel. Derivative of the last thing is 1. So right here, evaluating from 0 to 2, the fact that there's a 0 here and we have just x to a bunch of numbers is convenient for simplification purposes. And we'll see why in a moment. But when x equals 2, what do we get? 16 minus 3/2 of 4, 1/2 of 4 is 6. And there's a negative. Negative 2/3, 2 to the 3/2. I'll just write that like that for now. And then plus 2. And now we need to subtract what we get when we evaluate at 0. When we put 0 in, we get 0 minus 0 minus 0 plus 0, which is 0, which is nice for a problem like this. And now we'll just combine all the numbers. 16 and 2 make 18. 18 minus 6 makes 12. And this 2 to the 3/2, there are a couple different ways you could write it. You could just leave it as that. You could write it as, what, 2√2? I'm just going to write it as the square root of 8, because 2 cubed is 8. But you could write it. Some people would want that root 8. Some people would want that root 8 written as 2√2. And whichever way you want to write 2 to the 3/2 is fine with me, just as long as it's not the incorrect decimal. So any questions about part B?
Well, Professor,
Yes.
for part B, I got like I got 12 minus 4 times the square root of 2/3. Is that
Yeah, you
like
can-
an equivalent? Also, just to clarify, you said we're supposed to kind of, because I was gonna convert it to like a decimal, but then I remember you saying that.
Well,
you
that would
shouldn't
be
use
incorrect,
decimals.
because that can't be written as a decimal exactly. So the decimal is incorrect. We want the exact.
If I get an
Decimal
answer,
approximations are not correct.
so if I make a decimal approximation, then do you want us to avoid writing decimals as answers? Because I also make sure I don't get anything wrong.
Unless they're exact decimals. So the square root of 2 can't be written as an exact decimal. If you had 3/2 and you wrote your answer as 1.5, that would be okay, because they are exact. But the square root of 2 can't be written as a decimal. Well, it can't be written as a terminating decimal. So we want the exact answers. Well, I want the exact answers. We, in math in general, want the exact answers. But yeah, you could write this as, 4√2 on top. You can write it as just that entire thing, as long as it's exact. Any other questions about part B? So in part B, it was convenient that when we evaluated at 0, we got 0 because it gave us less to think about. And it can be tempting to think that when you have a 0 as one of your bounds, it'll always evaluate to 0, as it did in part B. But that's why we have part C here. Part C, integral from 0 to 3 of e to the x minus x. So here we need a function whose derivative is e to the x. Well, e to the x, the derivative of e to the x is e to the x. For the next piece, we have a power rule. The exponent is 1. 1 plus 1 is 2. So we get a half x squared. The derivative of this function is e to the x minus x. And we're evaluating here from 0 to 3. So what do we get when we substitute 3? E cubed. 3 squared is 9. So e cubed minus 9 halves. And then we subtract what we get when we evaluate 0. Notice here when we evaluated 0, we don't just get 0 because e to the 0 is 1. E to the 0 is 1, but 0 squared is 0. So that piece will be a 0. But now we just have to combine our numbers. Negative 9 halves minus 1. Negative 9 halves minus 2 more halves gives you negative 11 halves. Any questions about this one? Part D. What did I put? So part D, we have the integral from 1 to 2 of x plus 1 over x with respect to x. Now, we can't just go into the quotient and take it one piece at a time. There's no way to do that with when finding antiderivatives. But what we can do is split this fraction. X divided by x is 1. 1 divided by x is 1 over x. So here we can now do this definite integral by finding an indefinite integral one piece at a time. The derivative of x is 1. So with the constant rule, we get 1 times x. The derivative of log x is 1 over x. In this example, you technically don't need the absolute value because these are all positive numbers. But I am going to throw the absolute value there in case negative numbers show up. But here, we're evaluating from 1 to 2. And what do we get? Well, let's see what we get. Substitute 2, you get 2 plus natural log 2. Substitute 1, you get 1 plus the natural log of 1. Natural log 1, remember, is 0 because e to the 0 is 1. So that's a 0, 2 minus 1 is 1, and log 2 is log 2. Natural log 2.
Professor.
Yes.
Can you explain how you got rid of the fraction? I didn't get that. I didn't understand
Yeah.
that.
So this fraction can be split across the sum, meaning we can take it as x divided by x. So this first piece, x divided by x plus that next piece. And then x divided by x is 1. Is there another one? No, that's the only time that shows up on this worksheet.
Professor.
Yes.
When you do like the problems, is there any way that you could show the algebra? Because sometimes when I'm looking, I get lost in the steps because sometimes the algebra is kind of skips.
Well, we saw this last week, so that's considered side work as far as the calculus is concerned. Are there any other questions about part D. Part E. E. Integral from, here we have pi over 6 to pi over 4. And what do we have? 4 sine x minus cosecant squared of x. So here we have some trig functions. And in this case, both of these we can find antiderivatives of. How can we do that? Well, does this work? The derivative of cosine is negative sine. So that doesn't work. But if we throw a negative on it, the derivative of cosine, negative sine, the negatives cancel. So we get 4 sine. For the next piece, we need a function whose derivative is negative cosecant squared. The derivative of cotangent x is negative cosecant squared. And here we're evaluating from pi over 6. I just walked into the table. Okay. From pi over 6 to pi over 4. And we could go straight into the evaluation, but I'm just going to flip these two around so the negative is in the middle. Meaning I'm just going to write cotangent first. So pi over 6. So now we need to evaluate pi over 6 and pi over 4 and subtract. I'm going to do that at the top of the board since there's a glare down here from the sun. I think that suggests this is the first time all semester the sun has been out during this exact time on Thursday. Evaluated pi over 4. Well, I guess it doesn't because of daylight savings time. Evaluate pi over 4, we get cotangent of pi over 4 minus 4 cosine pi over 4. And we need to subtract the evaluation at pi over 6. So we have all of these trig functions to evaluate. So we need, well, triangles. We need the one with pi over 4s first. Pi over 4 and pi over 6 are first quadrant angles, so all we need is to directly use the triangles. Tangent is opposite over adjacent, so cotangent adjacent over opposite, 1 over 1. Cosine pi over 4, cosine adjacent over hypotenuse. Adjacent is 1, hypotenuse is √2. So we get 1 over √2, but then we have a negative 4 there. So we need negative 4, 1 over √2s. Minus, we need the other triangle now, so I'm going to erase here. We have 1 with pi over 6, so we have 1 to √3 to 2. Cotangent again is adjacent over opposite. Adjacent over opposite is √3 over 1, which is √3. And cosine is adjacent over hypotenuse. So for cosine, what do we get? We get √3 over 2 with a negative 4 on it. Or on it. Negative 4 of those is just negative 2. Negative 4 over 2 is negative 2. So now we'll just combine the like terms. This, you can leave it as 4 over root 2. That's perfectly fine with me. I don't think I've ever, deducted for the form of a square root, as long as it was a proper form. So that's okay. You can leave it as 4 over root 2. I'm just going to write it as 2 root 2 because I think that looks nicer. And then in here, how many square roots of 3? Well, if we have 1 and we take away 2, we're left with -1. And -1 with another negative makes a positive. And so some of these, with trig, you could have a fair amount of number manipulation toward the end. Any question? What was that? Part E. Any questions about part E? Part F.
Professor,
Yes.
Professor. So I think I understand how the sine became -4 cos x, because yeah.
So we needed there a function whose derivative was 4 sine x. So you could do it like this. You could pull out the 4 and then directly using the indefinite integral rules, the indefinite integral of sine x is negative cosine x, which made it -4 cosine x. Another way of observing that it's negative is by taking the derivative here. The derivative of just cosine x is negative sine x, and then the negatives cancel. So you could think of it either way, using pulling the 4 out and then using the indefinite integrals, or taking 4 cosine and making it negative if necessary. Any other questions about part E? So part F, we have 2 over 1 plus x squared. So here, if that 2 weren't there and it were a 1, it would be just the inverse tangent of x, because the derivative of inverse tangent is 1 over 1 plus x squared. But there's a 2 there, so we're going to need a 2 here. The derivative of 2 inverse tangents x is 2 times 1 over 1 plus x squared. And here we're evaluating from 0 to 1. How do we evaluate this? Well, that triangle. You could factor out a 2. I'm not going to. 2 inverse tangent of 1 minus 2 inverse tangent of 0. The angle whose tangent is 1, well, tangent of pi over 4 is 1 over 1, which is 1. The angle whose tangent is 0 and is within what quadrants 1 and 4. At angle 0, sine is 0, cosine is 1. So tangent is 0. So we get 2 pi over 4 minus 0. 2/4 is 1/2. Any questions about part F?
Could you repeat the step from 210 to the power of -1? Can you explain the whole thing again? Not the whole equation, but the first. Can you explain the two steps, the two previous steps again?
Do you mean going from here to here?
No, from there to the other down there.
From here to here?
Yep.
So we need here the angle whose tangent is 1. And from this triangle, the tangent of pi/4 is 1. So the angle whose tangent is 1 is pi/4. For this next one, we need the angle whose tangent is 0. And the tangent of 0 is sine of 0 over cosine 0, 0 over 1, which is 0. So the angle whose tangent is 1 pi/4. Any other questions about part F? So number 2 here, there are several consequences of the first part of the fundamental theorem of calculus. One of them is that we can take derivatives of definite integrals. Well, so long as the definite integral is a function of x. And in parts C and D, there are typos. They're not good typos either. We'll get there. I noticed them this morning. Those same typos do not show up on the homework, and they won't show up on the test. I guess I was more careless than I should have been in doing the worksheet. So here for part A, well, for all of them, we're going to see how we can use the fundamental theorem of calculus to take the derivative of a definite integral. For parts A and B, technically D as well, there are two different ways we could go about doing this. And I'll show both ways for parts A and B. So first, if we want f prime of x here, first, we'll use the fundamental theorem of calculus part 1, which tells us that a definite integral from a number to a single x, the derivative of that, in a way, cancels out. Meaning, we can take the derivative of this integral by treating this function as a function of x. Maybe alternatively, we compute. Any questions about using the first part of the fundamental theorem of calculus for this question, for this function, I should say? So for A and B, at the end of lecture 13.1, I mentioned the first two of these could be done directly, meaning, well, meaning without using the first part of the fundamental theorem of calculus, in particular, by using the second part and then taking a derivative. Why does that work here? Well, it works here because we can find a function whose derivative is 1 over 1 plus t squared. The derivative of the inverse tangent of t. I should write t like that. Inverse tangent of t. By the second part of the fundamental theorem of calculus, evaluate from 1 to x. And what does this equal? The inverse tangent of x minus the inverse tangent of 1. Is that showing up on the screen? Yeah. So we were able to compute that definite integral using the second part of the fundamental theorem of calculus. And because of that, we can now find capital F prime. So I'll say capital F prime. What is it? Well, derivative of inverse tangent x, 1 over 1 plus x squared. Inverse tangent of 1 over there, yeah, that does simplify to pi over 4. I'm not too concerned about that because I knew we were going to take its derivative. Yeah, the derivative of pi over 4 is 0, but less specifically, this is a constant over here, and its derivative is 0. And that does equal 1 over 1 plus x squared, as we knew it should equal using the first part of the fundamental theorem of calculus. So when you can do the integral, you can, well, maybe I should say, when you can find an antiderivative of the integrand, you can go through this using the first part of the fundamental theorem of calculus. And this one demonstrates, because that's just an x up there, it demonstrates how what we're really doing is showing that the definite integral, meaning, well, shows how the antiderivative going here and then taking the derivative of that in a way cancels out. You don't have to show both ways. But any questions about 2 part A?
Oh, so for for derivative of the big F,
Yes.
how come there isn't any? How come there isn't any? How come we didn't substitute the X for something? Wait,
In which one? In the first one or the first way or the second way?
the second way, one after you found the derivative of not derivative,
Well,
after
we
you
didn't
found
need to substitute. We just needed, all we need to do is find the derivative of this function.
oh, cool.
Any other questions about part A? And you can also see in the statement of the fundamental theorem of calculus, this is a 1 here, but in general, that just has to be a number at which the integrand and its antiderivative are defined. And you can see if that 1 were any other number, this piece would still be a constant and its derivative would still be 0.
So is the 10 to the power of -1 x, is that the derivative or the antiderivative of big F?
That is big F. It's an intermediate step in finding F prime. But in this case, F does just equal that function. Any other questions about part A? Okay, part B, the only difference, that is correct, the only difference. Yeah, the only difference is that our upper limit is now x squared. Now, how does that change this? Well, I will show both ways for this one. as I did for part A. So first, but I won't be able to fit them both on one board. We'll use the first part found out there of calculus. Now, the first part says we can take f prime when this upper limit is a single variable to the first power. So we can use a u substitution to force f to be of that form. So here, we'll let u equal x squared. And what happens if we do this? Well, then f is a function of u. And it's what? 1 to u, 1 plus t squared with respect to t. And now we can find df du and du dx. And if we find df du dx, then we can multiply them to give us df dx, the same as f prime of x. By the first part, found out there in our calculus, df du, 1 over 1 plus u squared. Du dx is just 2x. So df, well, maybe I'll say, so f prime of x, since that's what the direction said. Is that, yeah, the camera's low enough. F prime of x, same as df dx, which here, by chain rule, df du, du dx equals 1 over 1 plus u squared times 2x. And we'll get rid of u there because u equals x squared. We can do that and write it as one fraction. And we get 2x over 1 plus x to the 4. That's 1. Any questions about that one?
Yeah, sorry, I missed how you got 1 over 1 plus x to the 4th, like just the to the 4th part.
Yes. So we have u squared here. U is x squared. X squared squared. 4x's, so x to the 4th.
Oh, got it. Thank you.
You could say, what, an exponent rule would be 2 times 2. I think that's hard to remember. I think it's easier to just see a couple x squared sitting next to each other. And then say, oh, well, that's 4. Any other questions about using the first part from out there of calculus here? Okay, so let's show how we could do it directly, which we can do with this one because, because we could, actually before that, maybe I should make this comment since I'm going to point at this soon. Notice you could also arrive at this answer in a way similar to our other chain rule derivatives that we've done by treating this x squared as though it is just an x, meaning substitute an x squared in here, substitute an x squared, but then use the chain rule and multiply by the derivative of 2x. So you can do that, and in C and D, we will do that. I won't write out the substitution like we did for B. But we can take this derivative, or we can find this derivative directly, because we can apply the second part found out there in calculus here. So I'll say alternatively, what do we have? Well, f of x is what? Integral 1 to x squared of that. Well, derivative of inverse tangent t is 1 over 1 plus t squared. By the second part, I want that to be not my variable t, but that t. Inverse tangent of t from 1 to x squared. If we substitute, what do we get? We don't get that. We get the inverse tangent of x squared, I'll put that in parentheses, minus the inverse tangent 1, which is pi/4. So that's what f of x is. So capital F prime is what? Well, derivative of inverse tangent, 1 over 1 plus inside squared times derivative of the inside minus derivative of a constant. And that does equal what we expected. So you can see how the two seemingly different applications of chain rule result in the same, the same equation. And the two applications of chain rule in these two methods do result in the same thing. Any questions about part B? So parts A and B are convenient for illustrating how you could do it either way. Part C, well, that function is much harder, possibly impossible to find an antiderivative of. We'll find a convenient antiderivative of. So for part C, we will use the first part of the fundamental theorem of calculus directly. So what do we get? On my computer screen just flickered, it didn't. Well, maybe it did, my back was turned. Oh, so parts C and D do have typos. The bounds of integration those variables should be X. That typo does not show up on the homework, I made sure of that. Technically, if they were T, the answer for C and D would both be 0. So sorry about that. They should all be X's in the bounds. We have this function. So here we're going to use the first part of the fundamental theorem of calculus, but the first part applies only when the lower bound is a number and the upper bound is a function of X. Here, we don't have that. Here, we have the opposite. But what we can do is flip the bounds around so that our lower bound is a number and the upper bound is a function of X. That doesn't change the inside necessarily. But right now, this equals sign is not valid because we can't just flip sign or flip bounds around. There's a cost. If you want to flip the bounds around, you need to take a negative. But now we can find the derivative of this using first part of the fundamental theorem of calculus. All we have to do is remember that there's a negative there. How do we do that? Well, you could do substitution u equals cotangent and so on. I'm just going to say, so f prime of x equals what? Well, negative. How does it work? Well, take this, substitute it there for t. We have the negative. You could treat that negative as, writing the numerator as 7t cubed minus 2 if you want. Or the denominator. I'm just going to leave it like that. But we can't just apply the first part of the fundamental theorem of calculus when that's cotangent x. We also need to apply the chain rule, because this up here is more than just an x. So we need to multiply by the derivative of cotangent of x, which is negative cosecant squared of x. And you don't have to simplify. You don't have to write that as a fraction. We can just leave it like that. You can leave it like that. I am going to do one step in simplification because, those negatives cancel. Any questions about part C?
What about the lower bound, like 1? Why didn't we
Um,
evaluate the function?
The fundamental theorem of calculus applies no matter what that is, as long as it's a constant that the function is defined at. And when taking the derivative, that essentially turns into taking the derivative of a constant, meaning that turns into a difference of adding a 0 or subtracting a 0. So the lower bound, as long as it's a number, isn't going to contribute to the derivative in the same way that the derivative of a constant is 0. So in parts A and B, in the alternative method, the second method, the functions were all inverse tangent x minus inverse tangent of 1. And in taking this derivative, we had some function, 1 over 1 plus x squared, but the derivative of this second piece, which resulted from the lower bound, the derivative of that is 0. But in application of the first part directly, you don't even have to consider that piece. Any other questions about part C? Okay, so part D. In part D, we have functions which are supposed to be functions of x as our upper and lower bounds. And how is that treated? Well, we'll see. Integral from x to log x, supposed to be x's, 2t over t squared plus 1 with respect to t. So how are we going to do this? Well, the fundamental theorem of calculus, part 1, doesn't apply directly when we have, when one of our bounds isn't a constant. Here our bounds are x and log x, natural log x. But what we can do is split this integral at a constant using our fifth definite integral property. Meaning, instead of going from x to log x, we can go from x to some number, as long as the function is defined there. Here, if it were, I'll write this and then I'll say what I was about to say. We can split this at, say, 1. How does it split? Well, we're just splitting the area into 2 pieces. So we're squeezing 1 in between x and log x and breaking down our integral into these 2 pieces. Now, what number can you choose? If this were t squared minus 1, you couldn't choose 1 because the denominator is not defined there. So the number you choose, the only restriction on it is that the function, the integrand, has to be defined there. So here, the bottom is t squared plus 1. So you can put any real number in there. Now, if you want, you could say pi or √2 or something, or 30. But I'll choose 1. Now, we have two integrals here that we need to take the derivatives of. This one, we can apply the first part of fundamental theorem of calculus in the chain rule because the lower bound is a number, the upper bound is a function of x. But here, we're back in part C again, where we have the lower function being a function of x, the upper function being a number. So we need to flip that around by throwing a negative on it. Second one, we're just gonna not do anything with yet. And now the first part of the fundamental theorem of calculus does apply to both of these. And I'm going to write the answer at the top because I don't have much room at the bottom of the board. For this first part, notice it's just an x on top, so we don't need a chain rule.
Mr. Professor?
Yes.
Can you explain those two steps again? The first two steps. Of the
So
whole thing.
here we have x's on the top and bottom bounds. So we need to split the integral at some number. I chose to split at 1 because 1 is a number that the function is defined at. Well, that the inside of the integral is defined at. So instead of going from x to log x, splitting at 1 means we're going from x to 1 and then from 1 to log x.
But why? Because
Why? Well, we want to apply the first part of the fundamental theorem of calculus. And the first part doesn't apply directly when we have x's on the top and the bottom. The first part applies only when we have x's on the top and a number on the bottom. So our goal was to write that original integral as an integral where all we have are lower bounds being constants and upper bounds being functions of x. And to do that, we split the integral into the two pieces. Once we split it into two pieces, we then, this one was okay because we had a number on the bottom and x is on top, but here we have a number on top and an x on the bottom. So we had to flip that around. And to do that, we need a negative. So now, fundamental theorem of calculus does apply to both of these integrals. So now we need the derivatives of these. The fundamental theorem applies directly here with no use of the chain rule necessarily. We have a negative, replace all t's with x. And the fundamental theorem applies here, but we need to use the chain rule. So we'll replace all t's with log x. But then, sorry, 2 log x. There's a 2 there. But then we need to use the chain rule. The derivative of the natural log is 1 over x. And this one, it actually does simplify a little, but you don't have to worry about that. With these, it's sometimes more convenient to leave them like that. It's sometimes convenient to simplify them, but that's fine. Any questions about part D? Okay. Number 3. evaluate this integral. Using the second part of fundamental theorem of calculus. Well, the second part says take an antiderivative, evaluate at the endpoint. So what do we get? Third x cubed with a 2, half x squared with a 3, evaluate from 0 to 2. Evaluate at 2, what do we get? 8 times 2/3, 16/3. 4 times that 1.5 is 6 with a negative. Minus 0 minus 0, so that's if substituting 0 does give a 0 again here. 16/3 minus 6, 16/3 minus 18/3, negative 2/3. Any questions about part A? Okay, part B says using the limit definition. I went over that this morning and someone asked after we went over it, if it could show up on the final, and I said yes, it could. After that, sometime between 12 and 2, I decided I would not ask it on the final. So, the purpose of number 3 is to illustrate how convenient the fundamental theorem of calculus is, part 2 especially. I won't go over that here, and I won't ask it on the final. There are other things I'd rather ask. I made a general form of how I want the final to look, and I decided I didn't want one of these on it. But if you do want to see how it works, it will be in the other video. What is it, week? What week is this? 13. Workshop. Morning. So if you do want to see that limit, it's also similar to limits we did in week 4, 3, I think 4. So you can see that it takes, I don't know, 5 minutes maybe. But with these last 10 minutes, I would rather go over the problems we did not go over last week. Any questions about fundamental theorem of calculus? So you have a homework assignment due Monday on it. I tried to make it a shorter homework assignment than the others. Because I know many professors like cramming things into the last week. I don't know if it feels like this to any of the students, but I did set it up so that we would have comparatively less these last, actually the last 4 weeks. So you may have noticed the total lecture time was a little less. That was not unintentional. Hope it feels like that. But last week, there were 2 questions we didn't do. There was one, which I don't have written in front of me, so I have to remember it. Find the velocity function. Given an or find a position, did the same exact thing. Find the position function given an acceleration function of, it was definitely t squared. I think it was
I think it's 3 cosine t.
okay, there was a 3 there. Okay. Yes, there was. Thank you. Was there another number? No, it wasn't. But the next and the okay. Thank you. Okay. So last week we did find the velocity function. We got a velocity function last week of a third. t cubed minus 3 sine t plus 3. Yes. And we needed to then find a position function, which we could do. So I'll say worksheet 12, problem, I think it was 4. I did 3. So S of t we could find by taking the indefinite integral of velocity, but then using this condition to solve for the constant. And what do we get here? Well, a quarter, that gives us a quarter t to the 4th, a quarter times a 3rd is a 12th. We need a function whose derivative is negative 3 sine. Does 3 cosine t work? The derivative of cosine is negative sine. So it does work. Derivative of 3t is 3 plus a constant. And sometimes you'll see these constants written like C1 for the first one, C2 for the second one. In maybe a Calc 3 class or something else, I would concern myself more with differentiating between the constants. But here, you can just use C for both of them. Some people might say, oh, well, up here, C is already used, so we can't use it again. That's fine with me. This is a Calc 1 class, not a Math 400 class. So S of 0 equals 2. What does that tell us? Well, it tells us when t equals 0, the position is 2. So 2 equals substitute 0. 1/12 of 0 is 0. Plus 3 cosine of 0 is something. Plus 3 times 0 is 0. Plus c, what's cosine of 0? The x value over there, cosine of 0 is 1. Did that start off as negative 3 cosine t? I feel like c was supposed to be 5. Sorry. We found our velocity function was a positive there. Okay, that's where it went wrong. Sorry. The velocity function was 3 sine t. I should have noticed that. That's what I get for trying to remember. And that does change this to a negative because the derivative of cosine is negative sine. So negatives make a positive, which make that a negative 3, which makes that negative 3 times 1, negative 3. 2 equals c plus 3. So c equals 5. Which tells you the position function you wanted is a 12th t to the 4th minus 3 cosine t plus 3t with that c value, c equals 5. Any questions about that? Okay. So we also didn't do number 4 from worksheet 11. That might have been number 3 from worksheet 12. Yeah, it was number 3. Number 4 was definite intervals. So optimization questions, some of the computation could get pretty rough, but it's much easier if you're giving yourself enough space to work with. A cylindrical can with no top is to hold 8 cubic gallons of liquid. What dimensions minimize the cost of metal used to make such a can? Well, the metal that makes the can is going to make up the surface of the cylinder with no top. So 4 from worksheet 11. So here, we're doing calculus on the surface area of a cylinder, which remember is the rectangular shell, 2 pi RH, plus, in this case, there's no top, but there is a bottom. So the bottom has surface area pi r squared. We have this function, it's a function of r and h, but we're given a volume constraint. So 8 equals the volume of the cylinder, which is still pi r squared h. And we can use this to eliminate the variable h. Well, I'll just say h, solve for h, divide by pi r squared equals 8 over pi r squared. Now, why does that help us? Well, now we can write the surface area in terms of just r. So the surface area is 2 pi r times h plus pi r squared. And this does simplify nicely. 2 and 8 makes 16. Pi divided by pi cancels. R divided by r squared leaves us with 1 r in the bottom. And then we have plus pi r squared. So right now, our surface area is a function of one variable. So we need to take its derivative. I'm going to start that at the top of the page, the top of the board. I'm also going to write 16 over r second, and we'll see why in a moment. Well, we need the derivative, we need where it's 0, we need where it's undefined, then we need to show it gives a minimum. Here, the derivative, we have 2 pi r, 2r times pi, 2 pi r. Derivative here, we have 1 over r. Derivative of 1 over r is negative 1 over r squared. Notice this is undefined when the radius is 0, but that's not going to form a cylinder, so I'm not even going to consider it. So let's just set it equal to 0. When 2 pi r is 16 over r squared, multiplied by r squared, 2 pi r cubed equals 16. Solve this for r. What do you get? Well, you get r cubed. Divide by 2 pi, 16 over 2 is 8. Pi is still there. So r equals the cube root of 8 over pi. So right now, you could simplify that 2 over cube root of pi. That's fine. But right now, we need to show that this gives a minimum. I mean, it could, according to the calculus, give a maximum. Why does this give a minimum? I would normally write this under that. I'm going to write it over here instead. This gives a minimum. Well, when will it give a minimum? Well, you could do a decreasing, increasing argument. I'll use a concavity argument. The second derivative, we need it to be positive at that r value. What's the second derivative? 2 pi. Derivative of r to the negative 2, negative 2r to the negative 3. So we have that. So I'll just say here, avoiding the glare, this is positive when r equals the cube root of 8 over pi. Since it's positive, that'll give a minimum. And we look back at what the question asked, and we're still not done with it because it wants the dimensions of the cylinder, the radius and the height. Here's the radius. I'll just find the height over here. H equals what? 8 over pi times r squared. And you could leave your answer like that. I will simplify it here just because, well, I did this morning, so this does simplify to 2 over the cube root of pi. You could leave it like that. It does give a minimum. You don't need to find the volume. Any questions about that? So notice the reasoning for this one did follow similarly to the others, even though we had slightly less convenient equations. So any questions?
How did you get 2/3
How did I get 2/3? Where?
down
Oh.
for the?
Yeah, so it was 8 over pi r squared. So here we had 8 over pi all to the 1/3. Something to the 1/3 to the 2 gives us something to the 2/3. Any other questions about this one before the glare takes over the board? Okay, so I guess it's 3:15. I'll say something about the final in the next couple of weeks. Now, I will also say the same thing in an email later. There is one more topic which could show up on the final. I will, it's technically for next week. The homework assignment is not involved. It doesn't involve that topic, but I will post that video tonight. It's about a 25, 26-minute video. And that is the last topic. There will be a worksheet associated with that. We'll go over, I have it right here. There's one problem on it for next week. We'll go over it. There's also, tonight or tomorrow morning, I will send you an email with a list of the topics that could show up on the final, which won't be everything. It will be most of what we covered, but not everything. But we will also have 2 different review pages. One of them will look a lot like this, and it'll be called Homework and Exam Review. And this one we will go over on Thursday in addition to worksheet for next week. It has problems similar to the most missed homework, the most missed homework problems and the most missed exam problems. So we will go over that. Also, next week I will post a review, which is more of a semester review with all the types of problems we've seen that could show up on the final. And that I will post a document with solutions for that one. So everything I just said will be contained in an email. But you do have a homework assignment for Monday, which I do hope seems shorter than past homework assignments. Any questions?